What is Lewis structure? Electron dot structure, and dot represents what?
Representation for structures.
The dot, when you have a dot around the symbol, the dot is valence electrons. So look at your notes. What's the step, if you wanted to, we're just reviewing Lewis structure. So the first thing what you should do when you are writing Lewis structure, the first thing will be to arrange the atoms. Look at the notes, you have your notes. Arrange the atoms. So carbon, oxygen, carbon have in a center because carbon have to have a 4 bonds. Then what we should do? Count the total number of valence electrons. So we have 1 carbon. So how many electrons we have? And we have 2 hydrogens. So how many electrons? 2 hydrogens. 2 electrons. And we have 1 oxygen. How many electrons? 6. So the total number of valence electrons will be, when we add this up, will be 12. So now we have to distribute these electrons around the atoms, and we will put single bonds between atoms. So these are 2 electrons. So we already put it how many? 6. We have 6 more to put around. So we wanted to see that the hydrogen should have no more than 2 electrons. Our hydrogen already 2 electrons, so hydrogen is fine. Carbon and oxygen, the second row element, should obey octet rule. So we will put, is this right? It will have 6, 7, 8, 9, 10, 11, 12. So we have 12 electrons, but oxygen does not obey octet rule. Something wrong?
Carbon and oxygen be double bond?
Yes, so I'm getting to this. That's right, because now we distributed electrons, but now we are looking that oxygen does not obey octet rule. So what we will do, we'll take these electrons and move in between these 2 atoms. So then, now carbon and oxygen, that's good, obey the octet rule. So this will be the Lewis structure. Let's look at this. Is this Lewis structure? So what you should be sure that Lewis structure will have lone pair electrons. So that you show all lone pair electrons, and if the atoms, if you have overall charge, you have to place the charge on specific atom, formal charge. Here we don't, it's a neutral. But what's the formal charge? What is formal charge? It's a bookkeeping of electrons. So we're comparing atom, how many, what's the number of valence electron, and how many electrons are around this atom. If it's the same, then it's neutral. If it's less, positive charge. If it's around more than valence electrons, then will be negative charge. So let's calculate the formal charge on nitrogen. We know that this is like, we know that this oxygen does not have any formal charge, because from the first lecture we know that oxygen to neutral oxygen will have 2 bonds and 2 lone pair electrons. Carbon 4 bonds, so they are neutral. Now this nitrogen, what is the group number of nitrogen? Look at the periodic table. What is the group number? 5. So it means the nitrogen will have 5 valence electrons. And how many electrons are around nitrogen? How many electrons nitrogen own? Nitrogen own half bonding and all non-bonding. So here we have only bonding, so will be half. So half will be 4. Because non-bonding is 0 and bonding is 4. So the difference is +1. When we have a +1 or -1, we don't put 1. If you have +2, we'll put 2. But for 1, we just, so we'll have a nitrogen and we'll put positive charge. We can put positive charge on like that, or we can put circle around the positive charge. So this positive charge is on nitrogen. Hydrogens, we know 4 electrons, nitrogen are okay, they are neutral, no formal charge. So if we have molecular formula like this, think about in your notes and try to how many arrangements you can make. How many arrangements you can make for these atoms in this molecular formula? You can put like that. Six. One arrangement. Is this all, or we can arrange differently? Or we can put oxygen in between 2 carbons. And now calculate. So there are 2 arrangements possible, and you can calculate number of total valence electrons, distribute them, so hydrogen will have no more than 2, and the carbon and oxygen will obey octet rule. And you will get this 2. So sometimes for molecular formula, we can have not 1, but more good Lewis structures. They both are Lewis structure for this molecular formula. They have the same molecular formula, so that's why we call them isomers. This is specific type of isomer. They are constitutional isomers, or we can say structural isomers, because they have the same number of atoms, the same kind of atoms, but they have a different connection of atoms. So isomer, if they have the same number of atom, kind of atom, but they constitutional isomers, they have a different connection. But they should have the same number of total electrons. They are good Lewis structure for this molecular formula. but they are different compounds. They have a different name, they have a different chemical property, they are different compounds. And they have different physical and chemical properties different. Now, how many we can have different Lewis structure for this molecular formula? Think for a while. Look at your notes, write down and think by yourself. How many you can have different for this? If overall molecular formula has negative charge, it means that you have to add 1 electron to your total valence electrons. If it has a positive charge, you take away 1 electron. Now, the connection of the atom have to be the same, the only like that. Do you have like this? Carbon, nitrogen, hydrogen have to be on a side because they can make only 1 bond. Oxygen can be double bonded or single bonded because you can have overall negative charge. Like in molecular formula, overall negative charge. And these 2 possibilities are actually, they are the same molecule. They are different representation of Lewis structure, of the same Lewis structure, because these 2 are resonance contributor to the real structure. So we're using this arrow to show that these are 2 resonances of the same molecule. So are they in equilibrium? These 2? No, because they are not real, they don't exist. And if we will have something in equilibrium, we will use arrow like that or like this. This showing that these 2 structure in equilibrium, it means that they, once this, until they reach equilibrium, then both exist, but maybe in different concentration. So this arrow is telling us that these are not, they are in resonance, so they don't exist, they are not real structure. The real structure is hybrid of these 2. So how they are different? Look at this. What, do they have the same molecular formula? Yes. Do they have the same number of electrons? Total number of electrons? Yes. Do they have the same connection of atoms? Is the atom connected the same? Isomers, they will have a different connection for structural isomers. Are they connected the same? Oxygen to carbon, carbon to nitrogen and hydrogen, oxygen to carbon, carbon to nitrogen and hydrogen.
The single doubles make it,
A connection doesn't matter. This is number of electrons in between. So the connection is the same. What's the difference is the location of electrons, distribution of electrons. The only difference between these two, so the location of pi bond and the lone pair electrons. So the only difference. If they will be connected different, they will not be resonance structure. They will be isomers. So, or if they have the same molecular formula. So they are, only difference between these two is the location of a pi bond and lone pair electrons. And of course, the formal charge will change if the electrons will move. So if you will take these pi electrons and move to oxygen, these pi electrons will be lone pair electrons. And then the oxygen neutral will have 2 bonds to lone pair electrons, but oxygen with 1 bond and 3 pairs of lone pair electrons will have negative charge. And then if you move these electrons will come back. So now, because carbon will have to obey octet rule, so this pi, now carbon obey octet rule, and all the atoms obey octet rule. So how the hybrid looks like. Let's draw the hybrid of this two. So hybrid should have the same connection, the same single bonds, and the same connection as both of these. So I will exactly the same connection of atoms. Now we have to look at both structure between hydrogen and carbon. Between hydrogen and carbon, you have a single bond. So always have to be single bond in hybrid. Then between carbon and nitrogen, here is single bond, but here is double bond. So our mixture of two, the hybrid, will have partial double bond. Now between nitrogen and hydrogen, single bond will be single bond. Between carbon and oxygen, you have double bond and single bond. So the hybrid will have partial double bond. Now, lone pair electrons. On oxygen, here I have 2 pairs, here I have 3. I will put the lowest number. So I will put 2. On nitrogen, I have 2 and 1, so I will put just 1, lower number. Now the charges on the atom. Oxygen, no charge. Oxygen, negative charge. So the hybrid will have mixture of these two, so it will have partial negative charge. Carbon, no charge, no charge, no charge in hybrid. Nitrogen, negative charge, no charge. So nitrogen will have partial negative charge. And hydrogen, no charge. So this is the hybrid of these two resonance structure.
So the nitrogen has the same amount of electrons, but not the oxygen, or it doesn't have all 6 individual electrons?
This is partial double bond.
Right. I just wonder why we put 4 individual electrons instead of 6.
Because here we have a 4,
Right.
here we have a 6, we choose the lowest. Here we have a 2, here we have a 1, we choose the lowest.
So just the ones.
Yes.
Okay.
Because these are partial. So that's why we don't use the hybrid to count the electrons. That's why we will be, this is not a real structure, but we'll be using both structure because we can count electrons in both structure. And here it's hard when you have this partial. But in real structure, you don't have negative charge on nitrogen only or oxygen only. In real structure, negative charge is spread out on two atoms. Negative charge is spread out on nitrogen and oxygen, so this structure is more stable. If you spread out charge, make more stable, because it's not just in one point. So A and B are resonance structure. They are only difference between them is the position of a double bond and the position of the lone pair electrons. Is C, what's the C also resonance structure of A and B? What's the relationship between A and C?
That's a resonance structure.
Is C also resonance structure? I'm asking you. So the answer should be no, because you have unpaired electrons. So that's a different, completely, that's a radical, that's a different, completely compound. In all resonance structure, net charge should be the same and the same number of pairs. So you cannot have the radicals. Is this also resonance structure?
No.
No, because that's not right. It's carbon cannot have 5 bonds.
For the electric charge on the oxygen and nitrogen, how do you go about finding or figuring out where that negative charge is added onto?
You have to calculate formal charge. So if I will not have, we'll be doing this next. So if I will have this and I will make this structure by moving electrons, then I have to look at each atom and see is here on which atom I have a higher number of electrons now or lower when the valence electrons. So you have to calculate formal charge. So if you see oxygen, neutral, 2 bonds and 2 lone pair electrons. Oxygen with 1 bond and 3 pairs will have negative charge. You can check if you're not sure. We can calculate this. So oxygen, what's the group number? 6. So 6 valence electrons minus half bonding and all non-bonding. How many non-bonding you have? How many non-bonding? 6 and plus 1 because half bonding. So this will be 6 minus 7 is negative 1. So I calculated. So you have to check and calculate where now after where the formal charge will be. So the same here, you can calculate that nitrogen have to have formal negative charge. So we know already the hybrid, how it looks like, but now let's decide which A or B is more important for the hybrid. Which will be the major and minor. They sometimes can contribute 50-50 to the real structure, because real structure hybrid is a mixture of these two, but sometimes one will contribute more than the other. And so we have to decide which one is major and minor. Major will be the one that is the best. The best is the one that is most stable. And if you are looking at the structure, which one will be most stable? The more bonds, less charges, more stable. Obeying octet rule. If does not obey octet rule, it's unstable. Most stable if all atoms obey octet rule. And then the other thing is, it is most stable to have negative charge on more electronegative atom and positive charge on less electronegative atom. So which of this is most stable? The different charge, all obey octet rule. Negative charge on nitrogen, negative charge on oxygen. That's a major difference between these two. So which one is more electronegative, nitrogen or oxygen? Look at the periodic table. How electronegativity, that's why we will be looking at the periodic table all the time, because now electronegativity increasing from left to right and going and decreasing down the column. So oxygen is more electronegative, so it is more stable to have negative charge on more electronegative atom. So which one will be major? B. So B will be major contributor to the hybrid, and A is minor contributor. So it means the hybrid real structure is a mixture of these two, but will look more like B than A. Curve arrow. We will be using a lot of curve arrow in organic chemistry. So curve arrow the tail of arrow should start from electrons always. So, and this full arrow is showing where we're moving 2 electrons. And the head of arrow should show us where this electron are going. So for the resonance structure, the head should point on an atom or between the atom, not somewhere in space. It should point on an atom or between atom, because you can make the from pi bond lone pair electrons, so that will point on an atom if you're making lone pair electrons, or if you are making pi bond from lone pair electrons, it will point between atoms. So this a curve arrow, or you already have this curve arrow. So let's try to show how the other resonance structure will look like for the first one. So connection of atom is the same. So first I will, and single bond have to stay the same. So showing like this. This should not change in any resonance structure. So now I'm looking at these pi electrons are going between these 2 carbons. So I will not have a pi electrons here anymore in the second, because this is our second resonance structure. But this pi electrons now will be over there. And now I have to look at each atom and assign formal charges. So this carbon 4 minus, half bonding. Do you see that this hydrogen, this is the same as like that? Everybody see this? Because I don't know if you have, what's your preparation, but you know CH2 is the same as like that. So there's no, the carbon here, there's no any non-bonding electrons, but I have only 3 bonding electrons. So I have only 3 bonding, so what will be the charge on this carbon, formal charge? +1, so I will have to put positive charge on this carbon. So this is carbocation. This carbon, it's fine for bonds around, so neutral. I don't need to calculate because I see that for bonds. Hydrogen, okay. Now this carbon, how many bonds around?
4.
4. You know that this is single bond to one hydrogen, single bond to another hydrogen. So this carbon, no charge for bonds, it's neutral. So now in this structure, net charge +1, in another structure should have the same net charge because number of electrons should not change, only the location of the electrons change. So now I had positive charge on the last carbon, now I have positive charge on first carbon. Let's do the second example. So first connection of atoms. Exactly the same connection of atoms. This curved arrow is showing that these 2 electrons are going between these 2 carbons. So I will have pi bond between these 2 carbons. And the second arrow showing that these 2 electrons are going on oxygen. So oxygen before we had 2 lone pair electrons, but now we'll have 1 more because these 2 electrons are going on oxygen. So number of electrons is the same. Now we have to look at each atom and assign formal charges. So the carbon should be okay for bonds. This carbon is okay for bonds. This carbon for bonds. The only oxygen will have a formal charge. So what kind of formal charge on this oxygen? Will be 6 minus 6 non-bonding electrons and half bonding. So it will be -1. So this oxygen will have negative charge. So the formal charge will be on oxygen. Oxygen own more electrons than the valence electrons. So that's why negative charge. Let's do the last one. Connection of atoms the same. Now, these lone pair electrons are not changing, so should be the same. And the arrow is showing that these 2 electrons are going between these 2 atoms. Now I have to look at formal charges. This carbon for bonds, it's okay. Oxygen should have formal charge or not? Yes, because neutral oxygen, 2 bonds and 2 lone pair electrons. And this oxygen, 3 bonds, 1 lone pair electron. So that's not neutral. I have to assign formal charge on oxygen. So oxygen will be 6 minus 2 non-bonding and half bonding. Half bonding will be 3. So 6 minus 5 is positive one, we don't put one, so oxygen will have positive charge. Not enough electrons around oxygen. I have only 1, 2, 3, 4, 5 electrons, and I should have 6. So not enough. That's formal charge positive. I'm just bookkeeping electrons around atoms, these formal charges. And they are very important for us, because then we will have reaction whenever charge is up. Okay, and now which one is, looking at this two, which one is major, which one is minor for the top one? The first one, they are the same, so it means 50-50 contribution to the hybrid. The second one, which one will be major? The first one or the second? Second, because negative charge on more electronegative atom. And the last one will be which one? Positive charge on carbon, positive charge on oxygen. But where is the charge is less important, obeying octet rule is more important. So are all atoms obey octet rule here? Carbon is not. Are they all atoms obeying octet rule here? Yes. So this will be more stable, even that you have positive charge on more electronegative atom, but this is less important than obeying octet rule. So this will be less group work. Group work.